We all remember from geometry that the circumference of any circle is 2 pi r. When an object covers one round trip, we see that the velocity of the object is the distance the object travels, 2 pi r, divided by the period. So v equals 2 pi r over t.
Let's do an example. Suppose that the radius of the circular track is 100 meters instead. Same uber-mean machine, but now the track has a different radius. Let's say her centripetal acceleration is 246 meters per second squared. Then how long does it take her to go once around the track?
The question is asking us to find how long it takes for bright as light to go around the track one time. That's the period. So, first we know we have to use the equation v equals 2 pi r over t because we have to find t, the period. But we don't have the velocity yet. So, we can use our AVER equation, a sub c equals v squared over r, to find velocity, because we have the centripetal acceleration and the radius of the track.
To find velocity, all we have to do is plug into our equation a sub c equals v squared over r. A sub c, 246 meters per second squared, equals v squared over r, 100 meters. V squared equals 24,600 meters squared per second squared. So, v equals 157 meters per second.
Now that we have the velocity of bright as light's uber-mean machine, we can find the period by using our equation velocity v equals 2 times pi times the radius r over the period t.
We have v equals 2 pi r over t. Plug in the velocity v of 157 meters per second, and that equals 2 times pi times the radius r, 100 meters, and put that over the period t. Isolating t, we get that t equals 200 times pi meters over 157 meters per second. So it takes 4 seconds for bright as light to complete one orbit. That's once around the track.
Uniform circular motion occurs when an object moves around a circle with the radius r at a constant velocity v. The force that allows an object to follow this curved path is called the centripetal force, F sub c. The object's acceleration is directed toward the center of the circle and is called the centripetal acceleration, A sub c. And A sub c equals v squared over r.
The time it takes for the object to complete one orbit is the period, capital T, and the velocity of the object equals the circumference over the period, so v equals 2 pi r over capital T.
Section C, accelerated circular motion.
Uniform circular motion happens when an object moves around the circle at a constant speed. Accelerated circular motion happens when an object moving around a circle changes the magnitude of its velocity.
This type of acceleration is called tangential acceleration, a sub t. Tangential acceleration is always in the direction that the object is moving and is always tangent to the circle. So the vector of tangential acceleration, a sub t, is always tangent to the circle.
The tangential acceleration is positive if the object's velocity increases, and negative if the object's velocity decreases. The total acceleration of the object is the vector sum of the tangential acceleration and the centripetal acceleration. Remember that we can't add vectors using the regular old way. To find the magnitude of the vector sum, use the Pythagorean theorem.
Let's do an example of accelerated circular motion. Bright as light's cat, named Cat, enjoys chasing her tail. Her head moves in a circle with non-uniform acceleration.
Her head's total acceleration is 27 centimeters per second squared. The radius of the circle is 15 centimeters, and the velocity of Cat's head at the start is 12 centimeters per second. Find the tangential acceleration. Notice that everything we've been given is in centimeters, but acceleration is measured in meters per second squared. So in order to make our equation work, we need to convert our information from centimeters to meters.
Remember, 100 centimeters equal 1 meter. To convert centimeters to meters, we multiply the acceleration, 27 centimeters per second squared, times 1 meter over 100 centimeters, which equals 0.27 meters per second squared. And now, converting the radius and velocity, the radius equals 0.15 meters, and the initial velocity equals 0.12 meters per second.
Now that we got that covered, we know that A equals A sub t plus A sub c. We know what a is. We were given that in the problem. The head's total acceleration is 0.27 meters per second squared. The question asks us for tangential acceleration, a sub t. So let's find a sub c so we can figure this puppy, kitty, out.
Remember, we just showed you the equation for finding centripetal acceleration. A sub c equals v squared over r. Ever. A sub c equals v squared, 0.12 meters per second squared, over r, 0.15 meters. Dividing this out, we get that the centripetal acceleration equals 0.1 meters per second squared.
Now that we have a sub c and the total acceleration, we can use our equation to find the tangential acceleration. But realize that acceleration is a vector quantity, and we can't just use regular addition here. But lucky for us, we can use the Pythagorean theorem, because we can connect the vectors and make a right triangle to get the vectors' magnitudes. Of course, we're not going to draw the vectors because our standard deviant graphic artist is on a break. We're just trying to explain why we can use the Pythagorean theorem. Since vector A equals vector A sub t plus vector A sub c, the magnitude of A squared equals the magnitude of A sub t squared plus the magnitude of A sub c squared.
Using algebra to isolate a sub t squared, we get a sub t squared equals a squared minus a sub c squared. Now we can plug and chug.
A sub t squared equals 0.27 meters per second squared, quantity squared, minus 0.1 meters per second squared, quantity squared, which is 0.06 meters squared per second to the fourth. Take the square root of that to find a sub t, and we get that the tangential acceleration of Cat's head is 0.24 meters per second squared. And because the tangential acceleration is positive, we know that Cat's head is going faster and faster and faster and faster and faster!
Accelerated motion in a circle occurs when an object's velocity changes its magnitude. This type of acceleration is called tangential acceleration, a sub t. There are a few things we should know about tangential acceleration.
First, tangential acceleration is always tangent to the circle. Second, when an object's velocity increases, a sub t is positive. Third, when the velocity decreases, a sub t is negative. And finally, the total acceleration of an object in accelerated circular motion equals the vector sum of the tangential acceleration and the centripetal acceleration, or a equals a sub t plus a sub c.
Circular motion, no problem, right? Now let's move on to rotational motion.
Section D. Rotational motion.
All right, we've learned about objects that move in a circle. Now let's talk about rotational motion, objects that rotate about an axis. Think of an object that rotates, like a planet.
Rotating objects are described by the angle through which they rotate, theta. With the equations we'll learn in this section, we must use radians, represented by RAD, instead of degrees. So it's important to remember that when doing calculations with objects that rotate. Here's how we find the radian measurement of a circle.
If you have a circle with radius r and an arc of that circle s, then the angle in radians is the ratio of the arc divided by the radius. So the angle theta in radians equals s over r.
There are 360 degrees in a circle, and pi radians equals 180 degrees. So whenever we need to convert degrees into radians, or vice versa, use the ratio pi radians to 180 degrees.
But here's the tricky part. Radians are weird because they have no dimensions since they're defined by the ratio of two lengths. So when doing calculations with them, the rad part always drops out in the end, unless your answer is an angle that's supposed to be in radians.
Suppose you want to convert 270 degrees into radians.
Just multiply 270 degrees times pi radians divided by 180 degrees, and you get 4.7 radians.
But you said to dump those rads.
Only when you're not dealing in an angular quantity. A radian is an angular quantity, so keep it.
Keep me! Keep me!
Say the largest part of a little circle has a diameter of 0.04 meters. If we put a point on the edge of the circle here, and the circle turns through an angle of 30 degrees, how far does the point on the edge of the circle travel?
How far does it travel? We didn't learn the equation for that.
Actually, we did. There's a point going around in a circle. Whatever distance that point covers is the arc of the circle S.
Oh, okay. So we can use the equation theta equals S over R.
Right, but first we have to find the radius of the circle.
We were given the diameter d of the circle as 0.04 meters. Well, the diameter of a circle is twice the radius. So the radius equals the diameter, 0.04 meters, divided by 2, which is 0.02 meters.
All right, so we've solved for R and we got theta. All we have to do is plug in and solve for S in the equation theta equals S over R, right? Wrong. Remember that we can only use radians when using rotational motion equations.
So, because we were given theta in degrees, we have to convert degrees into radians in order to use our equation. So we have 30 degrees. Multiply that by pi radians over 180 degrees, and you get that 30 degrees equals 0.52 radians.
Now we can plug those numbers into the equation theta equals S over R. We're solving for S, so switch the equation around to get S equals R times theta. S equals 0.02 meters times 0.52 radians. Multiply and S equals 0.01, which means that the point on the edge of the circle traveled 0.01 meters.
So now we know how to find the distance a point on a rotating object travels when we use angles and radians. Now let's learn about the angular velocity of a rotating object. Don't worry, you'll like it.
The angular velocity of a rotating object, represented by the Greek letter little omega, is the angle theta, through which it turns over the time t it takes the object to turn. So, angular velocity has the unit of radians per second.
For example, if it takes 2 seconds for the little globe to turn through 25.2 radians, the angular velocity would be 25.2 radians over 2 seconds, or 12.6 radians per second.
If an object is moving with uniform speed, v, in a circle with radius r, then the distance, s, that the object travels is v times t. So let's see what we can do with this information.
Theta equals S over R. We showed you that equation a while ago. We also know that S equals VT. If we substitute VT for S, theta equals VT over R. Now, dividing both sides by t, we have theta over t equals V over R, because the t's cancel on the right. Okay, are you with us so far? Theta over t equals V over R. We just showed you the equation for angular velocity. Omega equals theta over t. So, if omega equals theta over t and theta over t equals V over R, another way of writing angular velocity is omega equals V over R.
This equation is usually rearranged and written as v equals omega times r, where v is the linear speed of a point on an object going around in a circle, omega is the angular velocity, and r is the radius of the object's path.
This equation is especially useful when speaking about a point that's a certain distance from the axis of rotation.
The axis of rotation is the axis about which all the objects of the rotating body are moving. For example, this is the axis of rotation of Earth, and the Earth is spinning about this axis.
In the equation v equals omega times r, v is directly proportional to r, because if the velocity increases, the radius will increase, and if the velocity decreases, the radius will decrease. So the farther a point on the object is from the axis, and the greater that point's radius, then the greater its linear speed.
Let's test this out. Let's find the linear speed, v, of a point on the little globe that's 0.005 meters from the axis when the globe is spinning at 7 radians per second.
Well, we're given the radius, r, of the point from the axis of rotation, 0.005 meters, and the angular velocity, omega, 7 radians per second. Plugging that into our equation of v equals omega times r, we get the linear speed of that point to be 0.035 meters per second.
Now compare that to a point that is farther away from the axis of rotation. Say there's a point that is 0.02 meters away from the axis of rotation, with the same angular velocity of 7 radians per second.
The linear speed equals the angular velocity, 7 radians per second, times the radius of 0.02 meters. And we get that v equals 0.14 meters per second.
Comparing this linear speed with that of the previous speed of 0.035 meters per second, we find that 0.14 meters per second is 4 times faster than when the point was closer to the axis of rotation. And that's because we're 4 times farther from the axis of rotation. So, if a point is 5 times farther from the axis of rotation, then the linear speed will be 5 times faster.
When an object rotates about an axis, that's called rotational motion. An object rotates through an angle, theta. Theta is measured in radians instead of degrees in rotational motion problems. There are pi radians in 180 degrees. In a circle with radius r and an arc s, theta in radians equals s over r.
The angular velocity of a rotating object, lowercase omega, is the angle through which it turns over the time it takes to turn, or omega equals theta over t. The linear speed of an object is directly proportional to how far the object is from the axis of rotation, the axis about which all objects are moving. This relationship is written as v equals omega times r.
Part 5. Linear momentum and Newton's laws of motion.
Remember Isaac Newton? You know, Mango Head? Well, in the late 17th century, he described 3 laws of motion. We don't know if he came up with these as a result of head trauma, but hey, they work. So live the laws, love the laws, be one with the laws.
But before we delve into Newton's laws of motion, we have to understand the principles behind them. And that comes from understanding the concepts of linear momentum and the conservation of linear momentum.
Section A. Linear momentum.
Have you ever been to a basketball game when 2 players are going for a loose ball and end up running into the photographers on the side? If both of them are going at the same speed, the one with more mass will be harder to stop, and the photographer he hits will probably have the bigger bruise.
This demonstrates the vector quantity called linear momentum. We represent the vector of linear momentum with a bold P.
Linear momentum P equals mass m times velocity v, or P equals mv. And the unit for momentum is the unit of mass, kilograms, times the unit of velocity, meters per second. So the unit of momentum is kilograms times meters over seconds.
So if the big basketball player runs off the court at 5 meters per second and has a mass of 90 kilograms, then what is his momentum?
Okay, we have the formula P equals mv, and we have the mass and velocity of the basketball player. So we have all the numbers we need to crank out an answer. Momentum, P, equals mass, 90 kilograms, times velocity, 5 meters per second, which is 450 kilogram meters per second.
So the momentum of that big ball player is 450 kilogram meters per second.
Section B, the principle of conservation of linear momentum.
Now for some fun stuff. We're going to talk about collisions. Things knocking into each other.
When 2 particles collide, the momentum of the whole system, that is, of what happens before, during, and after the collision, is the same before and after the collision. This is called the principle of the conservation of linear momentum.
Before we go on to explain the conservation of linear momentum, recognize that we will talk in terms of particles, because large objects and particles, like atoms and molecules, are both affected by this principle.
The principle of conservation of momentum says that the final momentum of the system equals the initial momentum of the system. Since P equals mv, if 2 particles collide, the mass of the first particle times its velocity before the collision plus the product of the mass and velocity of the second particle before the collision equals mass times velocity of the first particle after the collision plus the mass times velocity of the second particle after the collision, or m1 times v1 before plus m2 times v2 before equals m1 times v1 after plus m2 times v2 after. And the total linear momentum after minus the total linear momentum before is always 0. And that can be written as the change in momentum, delta p, equals 0.
The momentum after is the sum of the particles' momentum after the collision, or P after equals P sub 1 after plus P sub 2 after. And the momentum before is the sum of the particle's momentum before the collision. So, when we take the difference between these two, we get p after minus p before equals the quantity p sub 1 plus p sub 2 after minus the quantity p sub 1 plus p sub 2 before.
Okay, so we saw that the principle of conservation of linear momentum says that the final linear momentum equals the initial linear momentum, or delta p equals p after minus p before equals 0. If delta p equals 0, then delta p1 plus delta p2 also must always equal 0.
And if the linear momentum of particle 1 increases, then the linear momentum of particle 2 must decrease by exactly the same amount. That is, delta p2 equals negative delta p1.
So let's go back to our basketball players. Let's say the smaller player's on a fast break, and the bigger player's the only defender between the smaller player and the basket. So he decides to stop him by running right into him. I have a feeling that might be an intentional foul.
So he collides with him. If going toward the basket is the positive direction, and we know his mass is 90 kilograms, let's say his velocity before the collision was negative 2 meters per second. Negative because he was running away from the basket, and his velocity as he falls back is positive 2 meters per second. If the smaller player's mass is 55 kilograms, and his velocity before the collision was 6 meters per second, then what is his velocity after the collision?
First, we know that the momentum of the system is unchanged by the collision. Let's call the big player 1 and the smaller player 2. Since P equals mv, the momentum of the bigger player before the collision equals his mass times his velocity before the collision. So, P1 before equals mass, 90 kilograms, times V before, negative 2 meters per second, because the bigger player is moving away from the basket. And we get that P1 before equals negative 180 kilogram meters per second.
Doing the same thing for the bigger player's momentum after the collision, we get that P1 after equals his mass times his velocity after the collision. Plug and chug, and we get that P1 after equals 90 kilograms times positive 2 meters per second because he's falling towards the basket, and that equals 180 kilogram meters per second.
Now that we've got the bigger player's momentum before and after the collision, we can find the change in his momentum, and then eventually use that to find out the velocity of the smaller player after the collision.
So the change in momentum for the bigger player is the momentum after minus the momentum before, or delta P1 equals P1 after minus P1 before. So delta P1 equals 180 kilogram meters per second minus negative 180 kilogram meters per second, which is 360 kilogram meters per second.
Now let's find out the momentum of the smaller player before the collision.
Well, his momentum, P2, before equals his mass times his velocity before the collision. That's 55 kilograms times 6 meters per second. So, his momentum before the collision is 330 kilogram meters per second.
But the problem asks us to find his velocity after the collision. Since we don't know that yet, let's just set up the equation to find his velocity after the collision. Since P equals mv, his momentum after the collision, P2 after equals his mass times velocity after the collision, mv2 after. Plugging in his mass, 55 kilograms, P2 after equals 55 kilograms times V2 after.
We can figure out velocity after the collision using the principle of conservation of linear momentum. We know that the change of momentum of player 2 equals the negative change of momentum of player 1, or delta P2 equals negative delta P1. We also know that delta P2 equals P2 after minus P2 before. We already found delta P1, 360 kilogram meters per second. So to find delta P2, all we need to do is make that a negative. Plug that into our other equation, and we see that delta P2, negative 360 kilogram meters per second, equals P2 after minus P2 before. We already found P2 before to be 330 kilogram meters per second. So in order to find player 2's velocity after the collision, we need to solve for delta P2 after. Remember that delta P2 after equals m times V2 after, and the mass of player 2 equals 55 kilograms.
Plugging and chugging, we have 55 kilograms times the velocity of player 2 after, minus 330 kilogram meters per second equals negative 360 kilogram meters per second.
That's 55 kilograms times V2 after equals negative 30 kilogram meters per second. And solving for V2 after, we get negative 0.